All right, let's go ahead and get started. Who wants to ask the first question? Yes.
What is a black body, and be familiar with Wien's law and the Stefan-Boltzmann law?
What is a black body? And be familiar with Wien's law, Stefan's law. So remember, black body. This is what is this, chapter 5? Is that right? Yeah. So, excuse me. Black body's ideal, perfect emitter and absorber of radiation, and we call it a black body because if it's cool enough that it's not emitting any visible light, it would look as black could be, because it would be absorbing 100% of the photons falling on it and giving off no visible light photons. Black bodies always absorb 100% of the radiation that falls on them. They give off a characteristic spectrum that only depends on the temperature, and that has two important properties associated with it: Wien's law, Stefan-Boltzmann law. So Stefan-Boltzmann law is the one that says that the flux is sigma times T to the 4th power, right? So that if you were to double the temperature, the flux would increase by a factor of 2 to the 4th, or 16, all that business. And Wien's law is the one that says that the temperature and the peak wavelength are related via the temperature is 2.9 times 10 to the 6 nanometer Kelvin over the peak wavelength. You could rearrange it to say the peak wavelength is 2.9 times 10 to the 6 nanometer Kelvin over the temperature. This is the one that says hotter means bluer. The hotter it is, the shorter the wavelength of peak emission. And so hotter stars or bluer stars is a reflection of Wien's law. So that's that fundamental radiation law stuff that we did early on. Any follow-ups on that? All right, next question. Yes?
Could you talk about the turn-off point on an HR diagram?
Turn-off point on an HR diagram, yeah. So that's, what chapter is that?
15.
15. I don't have them memorized. What chapter? I can largely know it, but I won't get it every time. So the turn-off point on an HR diagram is where the main sequence stops, because of the fact that, so it's turn-off point for a cluster's HR diagram. The idea is that if you have a cluster of stars, they're all born together. They're all brothers and sisters, if you will. They're all a litter of stars born from the same very large cloud of gas and dust that fragments and forms multiple stars. And the time that it takes stars to form is very small compared to how long they spend on the main sequence, how long they take before they run out of central hydrogen and start doing other things, start evolving off the main sequence. And so the idea is, if we have a bunch of stars in a cluster that are all essentially the same age, then, well, remember, what kind of star spends less time on the main sequence? A massive star or a low mass star? Which one goes off the main sequence quicker?
Massive star.
A massive star, right? Because even though they've got more fuel, they are fuel guzzlers. They burn through their fuel so much more rapidly than a low mass star does that it more than makes up for the extra fuel that they have. So the idea is, early on, you could imagine that the star cluster's HR diagram would have pretty much everybody along the main sequence, along the zero-age main sequence, when the stars are just starting on the main sequence. A little deceptive, because the highest mass stars reach the main sequence while the low mass stars would still be protostars, but ignore that. Imagine you came back 4 million years later. Obviously, you can't do this for any one cluster. We don't have that kind of time. But you can imagine, come back 4 billion years later, the most massive O and maybe B-type stars, these all be O-type stars, would have already burned through all of their central hydrogen fuel and moved off the main sequence. But the lower mass stars would still be on the main sequence. After 10 million years, still more stars at the upper end of the main sequence, O-type stars, B-type stars, would have left the main sequence because they went through all their central hydrogen fuel. 100 million years, you're missing even more of the main sequence. 1 billion years, you're missing even more of the main sequence as lower and lower mass stars have evolved off of the main sequence, have burned through their central hydrogen. The turnoff point is where the main sequence in the cluster ends. So for example, with this 1 billion year old cluster, the main sequence ends right there, and you can say that the stars are kind of turning off the main sequence. That's why we call it the turn-off point. Stars at that point are just now evolving off the main sequence, and so we can tell how old a star cluster is by where the turn-off point is on the main sequence. The lower down the turn-off point is, the older the cluster must be, because the older the cluster is, the lower and the lower mass stars are lower down on the main sequence that have had time to move off of the main sequence by exhausting all of their central hydrogen. And so this is the key to checking our models for stellar evolution, because we can do computer models that would predict how long stars of various masses would stay on the main sequence, would predict what cluster HR diagrams would look like after various numbers of years, and we get very good agreement between theoretical predictions of what cluster HR diagrams ought to look like at various stages, and what various HR diagrams for various star clusters do look like. And it goes both ways. Theoretical modeling allows us to say, okay, a star of spectral class G1, for example, lives so many billion years on the main sequence, and then if you find a star cluster where the turnoff point is around spectral class G1, those are the most massive, brightest stars still on the main sequence for the cluster, then you would know that that cluster's age is however long it takes G1 stars to move off of the main sequence. So that's what the turnoff point is, that's what its significance is. It allows us to figure out how star clusters are. Really what you do is something more sophisticated, where you fit the entire HR diagram of the star cluster to theoretical models of what they should look like at various ages. But at a first blush, essentially you can just say, well, where the turnoff point is will tell you how old the cluster is. Any follow-up on that? Does that do it for you? Do you have any more questions? Yeah. How about anybody else? Anybody want some more about that? Okay, if not, waiting for the next question. Surely somebody has another question. Yes?
Can you talk about stellar parallax and how they calculate that?
So stellar parallax is something that we observe more so than calculate. I mean, if I told you how far a star was away, you could calculate its parallax. In practice, what we'll do is we measure parallaxes and then determine how far away the star is. That's going to be chapter 15 as well, isn't it? So parallax is the apparent shifting back and forth on the sky of a star due to Earth's motion around the sun. And so basic picture is, here is star A, here is star B. Star A is closer to us, star B is twice as far away. This is definitely not to scale, because all stars are hundreds of thousands of times or more farther away from us than we are from the sun, but you couldn't possibly show that to scale on a picture like this. So here we have Earth today, Earth 6 months later. The line of sight from Earth to the star changes as we orbit the sun. And so that causes where the star appears in front of much more distant stars in the background, stars that are so far away that we can't see them shifting back and forth because they're so far away from us compared to our distance from the sun. We can see that the star will appear to shift back and forth relative to background stars, similar to the way that if you look at your thumb, blinking your eyes, first left, then right, left, right, left, right, your thumb appears to shift back and forth because the line of sight from your eye to your thumb is different for your right eye versus your left eye. Your brain uses this information all the time without you needing to be aware of it. It's doing the calculations in the background for you. Your brain uses your binocular vision, the fact that you've got two eyes, to give you depth perception. It looks at how the parallax for different things causes them to appear different in your two fields of vision from your two eyes, and uses that to generate depth perception when you've got both eyes open. It's why we have two eyes. Other creatures have two eyes on the side of their head to give them a 360-degree field of view. But for us, it was more useful to have depth perception, and so we've got two eyes for that reason. The further away a star is, the less the line of sight shifts as it goes around the sun. So the parallax is smaller as a result. And there's a very simple formula that relates the distance in parsecs to the parallax in arcseconds. Namely, the distance in parsecs is just the reciprocal of the parallax in arcseconds. And the parallax is defined to be half the angle by which the star shifts back and forth over the course of the year. So in other words, the parallax is for star A, this angle right here, the angle that is half the total that it shifts back and forth. And by definition, a parsec is the distance for which the parallax is 1 arcsecond. And from that, because if you double the distance, you'd only get half as much shift. You see that distance is 1 over parallax is what it comes down to. So, any follow-ups on that? Okay, next question. Yes?
Could you go over the cosmic background radiation, just like what it is and what it means?
Yep, what it is, what it means, yep. What about the cosmic microwave background? So, the cosmic microwave background is microwave radiation that comes to us from every direction in the sky. Back in the old days, before digital television, old analog televisions, I don't even know if you, I guess you're probably young enough. Did you ever see like an old analog television with an analog tuner? If you tuned it between the stations, there'd be snow, there'd be flickering all over the screen. Turns out that about 1% of the snow in an old analog television was detection of cosmic microwave background radiation by your television antenna. Can't do that anymore with digital televisions. They just give you blue screens when you're between channels. But oh well. In any case, the cosmic microwave background is left over from the cosmic fireball, so to speak. In other words, when the universe was young, it was hot, much denser than it is now on average. And so the universe was filled essentially with black body radiation after it was born, but as the universe expanded, the radiation cooled, the universe cooled because the photons got longer and longer in wavelength, being stretched by the expansion of the universe. Remember that before so-called recombination, before atoms were able to form, before the universe was 380,000 years old, and the temperature was more than 3,000 Kelvin, it was too hot for any atoms to form yet, and so the universe was filled with a plasma of nuclei and free electrons, electrons not attached to any atoms, and photons scatter off of electrons, and so before the first atoms formed, the universe was essentially opaque. You couldn't see very far through it if you were able to be there at the time. Obviously, nobody was there. But photons couldn't travel very far before scattering off of an electron. But then when recombination happened, when the universe was 380,000 years old, it had cooled to 3,000 Kelvin, and atoms were able to form for the first time. And when that happened, the universe became transparent, because remember, hydrogen atoms are only good at absorbing very specific wavelengths, not good at absorbing or scattering every wavelength like the free electrons were. And so you can think of the universe as having gone from foggy to clear when recombination happened. And when we see the cosmic microwave background radiation today, we are seeing photons which were around at the time of recombination and have been traveling through the universe essentially unimpeded since then, because the universe became transparent when recombination happened. And so when we see the cosmic microwave background, what we're doing is we're seeing photons coming from what we call the surface of last scattering. Or in other words, remember that as we look out into space, we are looking back in time. And so if we look back out far enough into space, we see back to the time when recombination happened. And we can't see any further out into the universe than that, because the universe was opaque before recombination. And so in every direction in the sky around us, we see a spherical surface that corresponds to recombination when the universe was 380,000 years old. And it's that surface that's 45 billion light years away from us in every direction, much further away in light years than the age of the universe, because of the fact that the universe is expanding this whole time. The universe has been expanding. So there's a surface about 45 billion light years away in every direction, from which those photons in the cosmic microwave background have been traveling to us ever since the time of recombination. 380,000-year-old universe when it reached 3,000 Kelvin. And so one major significance of the cosmic microwave background radiation is that its detection back in the 1960s is what convinced cosmologists that the Big Bang theory was correct and not any rival hypotheses that had been formulated, because the primary rival hypothesis, the steady state hypothesis, did not predict the existence of the cosmic microwave background radiation. Subsequently, we have used the WMAP and Planck satellites to measure tiny hot spots and cold spots, tiny fluctuations in the temperature, a few parts in 100,000 coming from different directions in the sky in the cosmic microwave background. And that has told us many things that we talked about in class. They are these ripples, if you will, in the cosmic microwave background are sound waves that were caught in the act at the time of recombination. The universe was filled with sound before recombination, and when it became transparent, that stopped, and so we got a snapshot of sound waves on that surface of last scattering from when the universe was only 380,000 years old. Those hot and cold spots later grew to be, the denser regions later grew to be clusters and superclusters of galaxies. And the size of the hot spots has told us that the universe is flat, because the hot spots look the size that we predict they should in a flat universe. In a curved universe, they would either look larger or smaller because of the curved paths of the photons traveling through a curved universe. But in fact, they look the size that they should in a flat universe, and so they told us that the universe was flat. And furthermore, they have told us that the proportion of, they're what has allowed us most reliably to determine the proportion of dark matter, dark energy, and baryonic matter in the universe, because it turns out that the size of temperature fluctuations of various angular scales is sensitively dependent on the fraction of dark energy, dark matter, and ordinary matter in the universe, because extrapolate that back to the time of recombination and before, and that would set up the conditions under which those sound waves in the early universe were propagating. And by comparing the data, the red dots, for the temperature fluctuation sizes as a function of angular scale on the sky, we find that the universe, the best fit model, shown in blue here, the best fit model, says that the universe is 68% dark energy at the current time, 27% dark matter, and 5% ordinary matter. So the cosmic microwave background has opened up an era of what we call precision cosmology, where we're able to answer questions about various cosmological parameters in much more detail than we were before the WMAP and Planck satellites were launched in order to make very precise measurements of tiny, tiny fluctuations in temperature of the cosmic microwave background in various directions. That was a very long answer to your question, but you asked me a very general question, and so I just held forth on various aspects of the cosmic microwave background. Want to know more? Anything else you think I need to say about that?
I think that was good.
Okay, anybody else have any questions about any of that? Yes?
Sorry, I know you said this. How many light years away is the?
It's about 45 billion light years away from us. Those photons have been traveling to us through a transparent universe, and the regions that they're coming from, that sphere on the sky, is about 45 billion light years away from us now. Now, it wasn't nearly that far away from us when the photons were emitted in our direction, but the expansion of the universe has carried that region that they came from to be about 45 billion light years away from us now. So in that sense, we're seeing a surface that's about 45 billion light years away from us. That's as far out into space as we can see in our universe. Our universe may well be infinite in size, but we can't see further than 45 billion light years, because if we look past 45 billion light years, we would be looking back to times when the universe was opaque, not transparent, and no photons from that era in the universe could have traveled straight through us, straight through to us, without bouncing off of electrons. And so the cosmic microwave background is photons that we're seeing from the last time they bounced off of electrons, just before the universe became transparent, when the first atoms formed, is what it comes down to. I'm going to double check while you're thinking of other questions that my phone is still recording here. Seems to be. Yeah. Yes.
What are the two main starting assumptions in the models of galaxy formation?
Two main starting assumptions is that there were these density fluctuations, right, slight density fluctations that we see relics of in the cosmic microwave background. And and then you're starting out with hydrogen and helium. So big clouds of hydrogen and helium that collected into these density fluctuations after the dark matter got there first. The dark matter would have coalesced in these density fluctuations earlier than the matter did, because the ordinary matter did, because the dark matter would be able to start coalescing before recombination, whereas ordinary matter, strongly interacting with photons and so forth, would not have been able to do that. And so the dark matter started the dark matter is what became denser in the density fluctuations fastest. And then it served to pull in ordinary matter that formed the galaxies and so forth. Yes?
When you say class, that we know that the universe is getting faster as it grows?
So we know based on our observations of white dwarf supernovae that the expansion of the universe is speeding up instead of slowing down. And what we mean by that is without dark energy, and dark energy, we've never directly observed dark energy. We infer the existence of dark energy from the fact that we get a good match with the temperature structure of the cosmic microwave background, and from the fact that the universe is accelerating. We don't know what dark energy is, but if we hypothesize that there is an energy intrinsically associated with empty space, that would cause the universe to accelerate instead of slowing down. Before these observations by two teams of scientists in the late 1990s, before those observations, cosmologists expected that the expansion of the universe would be slowing down, meaning any given galaxy that we observe today expanding away from us because of the expansion of space, if we came back in 1 billion years, we would expect that it would be moving away from us more slowly than it is today. And if we looked at it 1 billion years previous to today, it would have been moving away from us faster than it is now. That the speed any given galaxy is moving away from us would be decreasing with time. Instead, the opposite is happening. Instead, the rate at which the galaxies are moving away from us, any given galaxy is speeding up instead of slowing down. And that is explainable in general relativity if there is dark energy, if space has an energy associated with it intrinsically, just being a property of space, that it's full of this dark energy. And that's one of the most remarkable discoveries in astronomy in the last 20 years, or for that matter, any time. It's a remarkable discovery, but it seems to be correct. And it seems to be that more than 2/3 of the matter energy in the universe is in the form of this mysterious dark energy that we don't know what it is yet. So it's a Nobel Prize waiting to happen. Yes?
Can you go over what a starburst galaxy is?
Yeah, so a starburst galaxy, if you just kind of hear the name, starburst, right? Well, it makes me think of a candy, but at the same time, there's a burst of star formation happening in it. Stars are forming in it much more rapidly than they are in ordinary galaxies like the Milky Way. In ordinary spiral or irregular galaxies that have gas and dust and star formation. And starbursts can form because of interactions of galaxies with one another. If galaxies collide with one another, then their molecular clouds can slam into one another. The stars will miss one another because they're so small compared to how far apart they are. But molecular clouds, which are sites of star formation, are much larger compared to the distance between them. So if galaxies interact with one another, their molecular clouds can smack into one another and set up shock waves and touch off waves of star formation. Supernova shock waves in those waves of star formation can set off more star formation and so forth. When the Milky Way and Andromeda collide, for example, you would expect bursts of star formation to be associated with that. So a starburst galaxy is one that's forming stars much more rapidly than normal. It's self-limiting. We know it has to be a temporary stage because a galaxy couldn't form stars that fast forever. If a galaxy formed stars at that rate, it would quickly use up all of its gas and dust that could form stars. been much shorter than the lifetime of the universe. So it's self-limiting in that you get lots of bubbles being blown by supernovae that will tend to clear gas out and make the starburst stop eventually. But for a while, it's like fireworks, essentially. Very slow fireworks, but fireworks. Are you sure? Okay. Yes?
Why do neutron stars initially spin very rapidly?
Now, why do neutron stars initially spin very rapidly? So a neutron star starts as the degenerate iron core of a high mass star. And that degenerate iron core is supported by electron degeneracy pressure, which means essentially you can think of it as being like a white dwarf made of iron instead of carbon in the center of the star. And that means it's about the size of white dwarfs in general. How big is a white dwarf, roughly speaking? Name another object that's about the same size as a white dwarf.
Small city.
That's a neutron star, that's where we're headed. But before that, yeah, a white dwarf's about, a white dwarf is about the size of Earth. So the iron core is about the size of the Earth. Silicon fusing into iron in a shell surrounding the core keeps dumping fresh iron on it. White dwarfs have this funny property that the more massive they are, the smaller they get, because the gravity getting stronger means they have to crush themselves into a smaller and smaller size to get the pressure to be high enough to support their weight. But eventually, the iron core exceeds the Chandrasekhar limit, exceeds the white dwarf limit, it exceeds the amount of mass that can be supported by electron degeneracy pressure. And so in a fraction of a second, it goes from being the size of Earth to the size of a neutron star, which is about the size of a city. And so let's see, if we think in terms of the classic, the ice skater business, right? Before it collapses, the ice skater's arms, if you will, are outstretched. The mass is spread into a volume the size of the Earth. Very rapidly, the mass moves all into the center. So the moment of inertia goes down spectacularly. It greatly shrinks. And because of angular momentum conservation, if the moment of inertia, the measure of how far mass is distributed from the axis of rotation, goes down, the speed of rotation has to go up in order to compensate and keep the angular momentum constant. So in other words, bottom line is that they spin so rapidly because of angular momentum conservation. It's a much bigger effect than the skater, bringing in their arms and whipping around much faster, because they're going from the size of Earth to the size of a city. And so that's why when a neutron star is born, it's spinning many times per second, because it had to conserve angular momentum, because the core collapsed so rapidly that there was no way for any torques to have any significant effect during the collapse. And so it's like the skater bringing in their arms, only it's like that skater on steroids bringing in their arms. I mean, it's a huge effect as far as that's concerned. So that's why. Yes?
Can you explain the energy levels of an electron and how they're related to spectral lines?
Yep, so that goes back to chapter 5, yep. Light and matter, and of course it's very important to us because it's from their spectral lines that we know what stars are made of and in what proportions. And so remember that it goes back to the idea that we have to describe atoms via quantum mechanics. And so an electron isn't really a little point particle following a nice orbit around the nucleus like you often see pictures of. It's actually spread out, if you will, in the form of what we call a wave function. And An important property of the orbitals, the wave functions that the electrons are allowed to be described by in an atom, is that only certain energies are allowed. So unlike if I am walking along a plank where I could climb to any height that I like, and my potential energy, my gravitational potential energy would be increasing as I climbed higher and higher, the energy levels in the atom are more like rungs on a ladder or shelves on a bookcase, where our book here, War and Peace, is only allowed to be certain heights above the floor instead of any old height you like above the floor. So here, our edition of War and Peace only is allowed certain gravitational potential energies because it can only be on certain shelves, certain heights above the floor. Similarly, in an atom, the electron is only allowed to have certain energies, not just any old energy, because it's only allowed to have certain wave function shapes around the nucleus. And we can represent that with an energy level diagram where we just draw a horizontal line of various heights to represent the energies that the electron is allowed to have. And fundamental idea is that electrons can absorb photons and use the energy to jump from a lower energy level to a higher one, or they can jump from a higher energy to a lower level by giving off a photon. So here's an illustration of an atom, an imaginary atom that's only got two energy levels, E1 and E2, and here it's making it's emitting a photon by the electron going from energy level E2 to energy level E1, really from wave function shape associated with the second energy to the wave function shape associated with the first energy. And the energy of the photon is equal to how much energy the electron lost in doing that. In other words, it's equal to E2 minus E1. Photon's energy is E2 minus E1, and the wavelength is given by h times c divided by E2 minus E1. H times c is 1240 electron volt nanometers, as we said in class. And so, similarly, if a photon having that exact energy, E2 minus E1, comes along, then the electron can absorb it and move up to the higher energy level. What if a photon comes along whose energy is somewhere in between E2 minus E1? Is not E2 minus E1, it's some other energy value, okay? Maybe it's less than E2 minus E1. If a photon comes along and its energy is less than E2 minus E1, what happens to it when it hits the atom? Yeah.
It doesn't.
Yeah, the atom's like, right? It doesn't care, right? It turns out it might scatter off of it, but generally it doesn't care because it's only able to absorb, to eat photons that have just the right energy to cause a transition. So if the energy is too low, the atom's like, meh, don't bother me. If the energy is too high, the atom is like, meh, don't bother me. Unless the energy is so high that it's able to tear the electron off and ionize it, otherwise the atom's like, whatever. But if the photon's energy is just right, if it's equal to the difference between two of the allowed energy levels for the atom, then it can